According to the National Electrical Code, portable equipment is defined as equipment that can be easily moved from one place to another. For this type of installation, the NEC allows the use of flexible cords and cables such as so-cord, provided that they are protected from damage. In a scenario where the conveyor is portable, the 480 volts AC power can be supplied to the portable conveyor using so-cord with twist lock plugs between sections. However, it is important to ensure that the cords are properly supported and protected from damage to comply with the protection from damage requirement of the code. Now let's consider the scenario where the conveyor is bolted to the floor. If the 60-foot conveyor is bolted to the floor, it is no longer considered portable equipment and must be installed in accordance with the NEC requirements for fixed wiring. This means that conduit or other approved raceways must be used to protect the conductors supplying power to the conveyor. Based on the information provided, the safer and more code-compliant solution would be to run conduit or liquid-type flexible metal conduit to each end of the 60-foot conveyor and then jumper between the conveyors with short-circuit cables. This would provide adequate protection from damage to the power supply conductors. Some additional considerations need to be taken into account. Firstly, the length of the so-cord used for the jumpers should be kept as short as possible. Secondly, the so-cord should be of appropriate amperage and voltage rating for the load. Thirdly, the twist lock plugs and receptacles should be of the correct type and amperage rating. Fourthly, the conveyor should be grounded in accordance with the NEC requirements. Now let's elaborate on the first consideration, keeping the so-cord as short as possible. Excessively long cords can create tripping hazards and increase the risk of damage. Shorter cords also reduce voltage drop, ensuring that the motor receives the proper voltage for optimal performance. Minimizing the cord length contributes to a safer and more efficient electrical system. Moving on to the second consideration, the appropriate amperage and voltage rating of the so-cord is crucial for preventing overheating and potential fire hazards. The cord's amperage rating must be equal to or greater than the full load current of the motor it supplies. Similarly, the voltage rating must be at least as high as the system voltage, which is 480 volts AC in this case. Using a cord with insufficient ratings can lead to insulation breakdown, short circuits, and equipment failure. Understanding the third consideration, twist lock plugs and receptacles, ensures a secure and reliable connection. These connectors are designed to prevent accidental disconnection, which is particularly important in industrial settings where vibrations and movement can occur. The twist lock mechanism provides a positive locking action, maintaining a continuous electrical path. The plugs and receptacles must also be rated for the appropriate amperage and voltage to handle the motor's power requirements safely. Finally, grounding the conveyor in accordance with the NEC requirements is essential for protecting personnel from electrical shock. Grounding provides a low-resistance path for fault currents to flow back to the source, causing the circuit breaker to trip and to energize the circuit. This prevents dangerous voltage from appearing on the metal parts of the conveyor, which could pose a serious safety hazard. Grounding should be done in accordance with NEC Article 250, which specifies the requirements for grounding and bonding electrical systems. Further considerations related to the NEC may include, firstly, understanding Article 400, which covers the use and specifications for flexible cords and cables. It outlines the acceptable uses, restrictions, and ampacity requirements for various types of flexible cords, including so-cord. Ensure that the selected so-cord meets the specific requirements outlined in this article for the intended application. Secondly, review in Article 430, which provides comprehensive guidelines for motor circuits, including overload protection, short-circuit protection, and conductor sizing. It is essential to comply with these requirements to ensure the safe and reliable operation of the conveyor motor. Thirdly, referencing Article 670, which addresses the specific requirements for industrial machinery, including conveyors. This article provides additional guidance on wiring methods, disconnecting means, and grounding requirements for industrial equipment. Compliance with Article 670 helps ensure that the conveyor installation meets the specific safety standards for industrial environments. Fourthly, when choosing conduit, consider options such as rigid metal conduit, intermediate metal conduit, or electrical metallic tubing, depending on the specific application and environmental conditions. Ensure that the conduit is properly sized to accommodate the conductors and that it is installed in accordance with NEC Article 344, 342, or 358 respectively. Fifthly, when using liquid-tight flexible metal conduit, be sure to select fittings that are specifically designed for use with this type of conduit. These fittings provide a watertight seal, preventing moisture from entering the conduit and damaging the conductors. Install the liquid-tight flexible metal conduit in accordance with NEC Article 350. Sixthly, for the so-called jumpers, consider using strain relief connectors at both ends of the cord to prevent stress on the conductors and terminations. Strain relief connectors help to maintain the integrity of the electrical connections and prevent premature failure of the cord. Seventhly, properly labeling all electrical components, including the motor starter panel, conduit runs, and so-called connections. Clear labeling helps to identify the purpose of each component and simplifies troubleshooting and maintenance. Eighthly, ensure that all electrical work is performed by qualified personnel who are familiar with the NEC requirements and have the necessary skills and experience to perform the work safely. Improper electrical work can create safety hazards and lead to equipment damage or failure. Ninthly, after completing the electrical installation, thoroughly inspect the work to ensure that it complies with all applicable codes and standards. This includes verifying the grounding connections, conductor sizes, and overcurrent protection devices. Tenthly, regularly inspect and maintain the electrical system to identify and correct any potential problems before they can cause equipment failure or safety hazards. This includes checking for loose connections, damaged cords, and corroded components. Let's delve into grounding considerations in further detail. Grounding is a critical safety measure that protects personnel and equipment from electrical shock. In the context of a conveyor system, proper grounding ensures that any fault current, such as a short circuit, will have a low resistance path back to the source, causing the overcurrent protection device circuit breaker or fuse to trip and de-energize the circuit. This prevents dangerous voltage from appearing on the metal parts of the conveyor, which could pose a serious safety hazard. The NEC provides specific requirements for grounding electrical systems in Article 250. These requirements cover various aspects of grounding, including the size and type of grounding conductors, the methods for connecting grounding electrodes, and the bonding of metal enclosures and equipment. To properly ground a conveyor system, several key steps must be taken. Firstly, a grounding electrode system must be established. This typically involves connecting to a grounding electrode, such as a ground rod, metal water pipe, or building steel. The grounding electrode provides a reference point for the electrical system and helps to dissipate fault currents into the earth. Secondly, a grounding conductor must be run from the grounding electrode to the main electrical panel or service entrance. This conductor, known as the equipment grounding conductor, provides a low impedance path for fault currents to flow back to the source. Thirdly, all metal enclosures and equipment associated with the conveyor system, including the motor frame, control panels, and conduit, must be bonded together. Bonding ensures that all metal parts are at the same electrical potential, preventing voltage differences that could create a shock hazard. Fourthly, flexible metal conduit FMC and liquid-tight flexible metal conduit LFMC are commonly used for wiring conveyor systems. These types of conduit require special grounding considerations. When using FMC or LFMC, a separate equipment grounding conductor must be run inside the conduit to provide a reliable grounding path. The conduit itself cannot be used as the sole grounding conductor. Fifthly, twist lock plugs and receptacles used in the conveyor system must also be properly grounded. The grounding pin on the plug must be connected to the equipment grounding conductor, ensuring that the metal parts of the connected equipment are grounded. Sixthly, regularly inspect the grounding system to ensure that all connections are tight and free from corrosion. Loose or corroded connections can increase the resistance of the grounding path, reducing its effectiveness. Seventhly, ground resistance testing should be performed periodically to verify the integrity of the grounding system. This test measures the resistance between the grounding electrode and remote earth, providing an indication of the effectiveness of the grounding system. Eighthly, in addition to equipment grounding, personnel grounding is also an important consideration, especially in environments where static electricity can accumulate. Personnel grounding can be achieved through the use of conductive footwear, wrist straps, and grounding mats. Ninthly, ensure that all electrical work is performed by qualified personnel who are knowledgeable in grounding techniques and NEC requirements. Improper grounding can create serious safety hazards. Tenthly, the size of the equipment grounding conductor must be determined based on the size of the overcurrent protection device, circuit breaker, or fuse protecting the circuit. NEC Table 250.122 provides guidance on sizing equipment grounding conductors. Now, let's discuss specific considerations for using saw cord in conveyor systems. Saw cord is a type of flexible cord that is commonly used for portable equipment and appliances. It consists of stranded copper conductors insulated with rubber or thermoplastic material, surrounded by an outer jacket of oil-resistant rubber or thermoplastic. Saw cord is available in various sizes and configurations, with different numbers of conductors and ampacity ratings. When using saw cord in a conveyor system, there are several important factors to consider. Firstly, saw cord is permitted for use in portable equipment, such as conveyors that are easily moved from one location to another. However, it is not permitted for use as a substitute for fixed wiring in permanent installations. Secondly, the saw cord must be protected from physical damage. This can be achieved by routing the cord in a manner that minimizes exposure to abrasion, impact, and other hazards. Where the cord is subject to damage, it should be protected by conduit or other suitable means. Thirdly, the saw cord must be properly supported to prevent strain on the connections. This can be achieved by using strain relief connectors or other methods that secure the cord to the equipment. Fourthly, the saw cord must be of the appropriate size and ampacity rating for the load it will be carrying. The ampacity rating of the cord must be equal to or greater than the full load current of the motor or other equipment it supplies. Fifthly, the saw cord must be terminated properly using approved connectors and terminals. The connections must be tight and secure to prevent overheating and arcing. Sixthly, the saw cord must be grounded properly in accordance with NEC requirements. The equipment grounding conductor in the cord must be connected to the grounding terminal in the equipment and to the grounding system of the building. Seventhly, the length of the saw cord should be kept as short as possible to minimize voltage drop and prevent tripping hazards. Excessively long cords can also be more susceptible to damage. Eighthly, regularly inspect the saw cord for signs of damage such as cuts, abrasions, and frayed insulation. Damaged cord should be replaced immediately to prevent electrical hazards. Ninthly, when using saw cord in wet or damp locations, be sure to use cord that is listed for wet locations. This type of cord has a water-resistant outer jacket and is designed to withstand exposure to moisture. Tenthly, avoid running saw cord through doorways, windows, or other openings where it could be pinched or damaged. Also, avoid running cord across walkways or areas where it could be a tripping hazard.